In this video, we begin our discussion of how to find probabilities for a normal distribution. Once we determine that a variable follows a normal model, we typically compute probabilities by converting the original variable into a standardized form called a z-score. The key idea is that there are infinitely many normal distributions, each with its own mean and standard deviation. But there is only one standard normal distribution. By transforming our variable appropriately, we can use standard normal tables or software to find probabilities efficiently and consistently. This standardization step is the bridge that allows us to move from any normal model to the universal standard normal curve. Here we introduce the formula for the z-score. If the random variable x is normal with some mean mu and some standard deviation sigma, the standardized value corresponding to an observation x is given by z equal to x minus mu divided by sigma. This formula recenters the distribution at 0 and rescales it so the standard deviation becomes 1. After this transformation, the new variable z follows the standard normal distribution. This is extremely useful because we only need one set of probability tools for the standard normal rather than separate tools for every possible normal distribution. Why do we standardize in the first place? The main reason is convenience and consistency. By converting to the standard normal distribution, we can use pre-computed tables, statistical software, or calculators to find probabilities quickly. Another important point is that for continuous distributions like the normal, we always compute probabilities over intervals rather than at exact points. The area under the curve represents probability, so standardization simply helps us locate the correct area more easily. We now outline the overall step-by-step procedure. The first step is to clearly state the distribution and identify the mean and standard deviation. Writing the model explicitly helps prevent mistakes later. It also forces us to think carefully about what random variable we are working with and what probability the problem is asking us to compute. Skipping this step often leads to confusion, so it is a good habit to always begin by stating the model. In step 2, we draw a sketch of the normal curve. Even a rough bell curve can be extremely helpful. We label the mean and mark the value or values of interest, then shade the region corresponding to the desired probability. This visual step helps us determine whether we need an area to the left, to the right, or between two values. Many student errors come from skipping the sketch and misidentifying which probability to compute. Step 3 is to compute the z-scores. For each boundary value x, we apply the z-score formula. This converts the problem from the original scale into the standard normal scale. It is important to compute these carefully and keep track of the sign of the z-score, since positive and negative values correspond to different regions of the normal curve. Step 4 is to use a table or software. Most standard normal tables report the probability that standard normal random variable z is less than some value, that is, the area to the left of a given z value. If we need a right tail probability, we use the complement rule. For probabilities between two values, we subtract the two cumulative areas. Modern statistical software and calculators can perform these steps instantly, but it is still important to understand the underlying logic. The final step is interpretation. After computing the probability numerically, we must translate the answer back into the context of the original problem. This means restating the result using the original variable in units. In applied statistics, this interpretation step is essential for communicating results clearly and meaningfully. Now let's work through an example involving an antihypertensive drug. Suppose the reduction in systolic blood pressure follows a normal distribution with mean 10 and standard deviation 4. We are asked to find the probability that a randomly treated patient experiences a reduction of at least 15 millimeters of mercury. The key phrase here is at least, which tells us we are looking for a right tail probability. Our first computational step is to convert the value 15 into a z-score. Using the formula, we compute Z equal to 15 minus 10 divided by 4 is equal to 1.25. This tells us that a reduction of 15 millimeters of mercury is 1.25 standard deviations above the mean. Interpreting Z-scores in terms of standard deviations often provides useful intuition about how extreme a value is. Next, we use software, in this case the normal probability calculator in JUMP, to find the area to the right of Z equals 1.25. The calculator reports the probability equal to 0.1056. Visually, this corresponds to the shaded right tail beyond 1.25 on the standard normal curve. Using software greatly simplifies what would otherwise require careful table lookup. Alternatively, we could compute the probability directly in the normal calculator by entering the original mean and standard deviation without explicitly computing the Z-score first. Both approaches give the same result. Understanding both methods is helpful because different tools and exam settings may favor one approach over the other. Finally, we interpret the result in context. A probability of approximately 0.1056 means that about 10.6% of patients experience a reduction of at least 15 millimeters of mercury after taking the drug. Notice how the final answer is expressed in terms of patients and blood pressure reduction rather than in terms of Z-scores. This contextual interpretation is the final and essential step in any applied probability calculation.